Hi guys, welcome to the lesson of ordinary differential equations. So in this class, we are going to discuss about the mixing problem. So previously, we discussed the Torricelli's law. Now we are going to talk about this mixing problem. So the mixing problem is all about a chemical reaction. We can assume that there is a container containing some chemical. Let's call it a brine solution, for instance. And there is some solution in this tank. We can call initially it is V0 gallons. So this tank holds V0 gallons of the brine solution, and some liquid or the some solution liquid solution is uh, exiting out, and some solution is entering into the tank. So we can also say that in this V0 gallons, the solution contains some amount of salt. So let's call it A pounds. So this is amount of salt that is initially present in the tank. Now, a brine solution that is entering into this tank is containing B pounds of salt per gallon. Okay, so the solution that is entering, it contains B pound per gallons, and it's poured in the tank at some rate. Let's call it E gallons per minute. So this is the rate at which the solution is entering into the tank. So that is E gallons per minute. And while simultaneously the well-stirred solution leaves the tank at the rate of F gallon per minute. So it's leaving the tank with this flow rate that is F gallon per minute. So it's the rate out. So we can call it rate in, and this is rate out for the brine solution. Now let Q denotes the amount of salt. It is the amount of salt at any time t, that is present in the tank. All right, so the rate of change of this amount of salt can be given by rate of salt coming in minus rate of salt going out, right? So the amount of salt can be given by this expression at any time t. So we first need to calculate the volume of brine in the tank at any time t, which is the initial volume. So the volume of brine at any time t is equals to the initial volume that is present in the tank plus the volume of the brine that is added. So we can write it as E times T. That is the volume of the brine that is added, because E is the flow rate at which the brine solution is entering into the tank, and it's multiplied by time to get the volume, and then some volume is removed. So we can write minus, we can take a difference from this expression of the exiting volume. So that will be F times T, because F is the flow rate with which the solution is coming out, right? So this is the volume of brine at any time T in the tank. In the tank. All right, so this is the volume of the brine and the concentration of the salt in the tank. Now the concentration of the salt in the tank can be given by Q divided by this volume. All right, so it will be equals to Q divided by V naught plus ET minus FT. So that is the concentration of the salt at any time T in the tank, right? So the salt leaves the tank at the rate F times this concentration, that is Q over V naught plus ET minus FT. So this is the rate out of salt at any time T. It's given by F times this expression, that is the amount, the concentration of the salt. So now the expression dq over dt can be written as the rate in, that is B times E, where E is the rate of brine solution coming in and B is the concentration of the salt that is carried in this solution that is coming in. So, and we can write a pound of salt is already in the solution. Therefore, this is B times E, that is the rate of salt that is coming in, minus the rate of the salt that is going out, or we can say it leaving the tank. All right, so now this is the expression for the mixing problem, or we can say it as a dilution problem. It's also called a dilution problem. So using this expression, we can solve these chemical reaction problems or these mixing problems. So if we simplify this expression, we get this kind of expression. So where we are given with F, we are given with E, we are given with B, we are given with A, we need to find the concentration of the salt at any time T. F is flow rate that is coming out. So this is flow rate of the brine solution coming out. This is the flow rate coming in of the brine solution. And this is the amount of salt that is coming in, amount of salt that is coming into the tank with the brine solution, and initial concentration of salt in the tank. So these are given and we need to know this Q in terms of T. So let's start with some problem. Let's take an example of the mixing problem. A tank initially holds 100 gallon of brine. So there is a tank that holds 100 uh, gallons of brine. That is the initial volume of the brine solution. And solution containing 1 pound salt. So the initial concentration of the salt is given as 1 pound at t equals 0. So the initial condition, we can write that the amount of salt at time 0 is 1 pound, right? That is given by A. So another brine solution that is coming in containing 1 pound of salt per gallon. So B is given as 1 pound per gallon, and is poured into the tank at the rate of 3 gallon per minute. So its rate, that is flow rate, is 3 gallons per minute. So E is given, that is 3 gallons per minute. While the well-stirred mixture leaves the tank at the same rate, so the rate of exit is also same, that is 3 gallon per minute. So F is 3 gallon per minute, right? So it's in the condition of equilibrium, and we need to find the amount of salt in the tank at any time t, that is Q of t. So we need the expression for Q of t. Therefore, we already derived the expression as dq over dt plus fq over v naught plus et minus ft equals be. Now these are known, so we can plug in the values. F is given as 3 gallons per minute, and the initial volume is in the tank is 100 gallons, plus this is again 3t minus 3t, because rate in is 3, that is E is 3, F is 3, and equals to B is given as 1. So it's 3 times 1. Therefore, the expression becomes dq over dt plus 0.03 q equals 3. Now this is simply a linear equation. We can find the integrating factor for this equation, that will be exponential to the power integral of this function. So we will get e to the power 0.03 t, that is our integrating factor. So the solution will look like q times e to the power 0.03 t equals the integral of 3 e to the power 0.03 t dt. So we will get q equals 3 over 0.03 plus c e to the power negative 0.03 t. All right, so the initial condition is given. Okay, let's simplify this. So it will be 100 plus c e to the power negative 0.03 t. Now we can apply the initial condition to find the c. So the initial concentration at time 0 for the concentration of the salt is given as 1 pound. So a 1 equals 100 plus c e to the power 0, which implies that c equals negative 99, and plug in this value here. So it will be q of t equals 100 minus 99 times exponential to the power negative 0.03 times t. Now this is the expression for the Brine solution. So now the second thing we need to find is the time at which the mixture in the tank contains 2 pounds of salt. So we need to find the time at which the mixture in the tank will contain 2 pounds of salt. So this is the tank, and initially we said that there is a the tank brine solution contains 1 pound of the salt, but now we need to find the time at which the brine will be containing 2 pounds of the salt. So Q is given as 2 pound in this problem. So it's we can replace 2 for Q, and then we need to find the time. So we can just manipulate this mathematically. It will be 100, 2 minus 100, that is negative 98, and this is negative 99, so negative 99 in the divide and 0.03 t. Then we can simply take natural log on both sides, so it will be ln 98 over 99 equals negative 0.03. Okay, so negative 0.03 t, and we can simply write ln 98 over 99. So this will be some negative value because it's less than 1 divided by negative 0.03. So we will get t equals 0.338 minutes. So in this way, we can compute the amount of salt present in the tank at any time t. So in this case, it was pretty easy that the initial the flow rate in and flow rate out was equal, but in some cases you may experience that the flow rate and flow rate in and flow rate out of the brine solution is not equal. Then you are going to get differential equation of some kind. For instance, let's take an example that tank 50-gallon tank. We have a 50-gallon tank, so initial volume is 50 gallons. 50 gallons, and okay, so it's okay, the volume of the tank is 50 gallon, but not the initial volume of the water. So the initial volume of the solution, sorry, is 10 gallons. Okay, and it's fresh water, right? 50-gallon tank initially contains 10 gallon of fresh water. So we have a tank. The volume of the tank is 10 gallons. Sorry, 50 gallons. The volume of the tank is 50 gallons, but initially it contains 10 gallons of fresh water. All right, so there is no concentration of the salt right now. So at time t equals to 0, we can say that the concentration of salt, that is A, is equals to 0. And the brine solution containing 1 pound of salt per gallon. Okay, so B equals 1 pound per gallon is poured in the tank at the rate that is 4 gallon per minute. Okay, now with this given information, what we need is we need flow rate out. So while the well-stirred mixture leave the tank at the rate 2 gallon per minute. Okay, now the rate here is 2 gallons per minute. So we can see that this is not the equilibrium condition because the solution entering at 4 gallon per minute is exiting at 2 gallon per minute. So now we can form the differential equation with these given conditions. We have dq over dt plus FQ over V naught plus ET minus FT equals BE, where F is given as 2, so it will be 2Q over V naught, that is 10 gallons, plus ET, it will be 4T minus FT, it will be 2T, and B is given as 1 times E is 4. So here we get dq over dt plus 2q over 10 plus 2t equals to 4. Now we can find the integrating factor simply by raising it to the exponential, so it will be 1 over t plus 5 dt, so it will be e to the power ln t plus 5, that will be t plus 5. So the integrating factor in this case is t plus 5, therefore the expression will be q times t plus 5 equals 4 times t plus 5 integral dt. Now we have q times t plus 5 equals 4t squared over 2 plus 20t plus c. So we will get here is that q of t plus 5 equals 2t squared plus 20t plus c, and q equals 2t squared plus 20t plus c divided by 10, sorry, t plus 5. T plus 5, and the initial condition is given that there is no concentration of salt present in the tank, so q of 0 equals 0, which implies that we can find c. So it's 0 equals 0 plus 0 plus c divided by 0 plus 5, so which implies that c equals 0, so the expression becomes q of t equals 2t squared plus 20t divided by t plus 5. All right, so this is the simplified form of this equation after finding the constant of the integration. So now we can solve further problem which asks that the amount of time required for overflow to occur. Okay, so we need to find the time at which it will like overflow, the tank will overflow. So the time required for the tank to overflow will be 10 plus 2t equals to 50, because the total volume of the tank is 50 gallons. Therefore, this is the initial volume, and this is the initial volume that is given that the tank is carrying initially V naught, and plus twice of the t, because this 2t is actually the difference of flow in and flow out. So this is the flow rate in and flow rate out, that is 2t. So the total volume, this is the total volume, and when it will be equals to 50, which means that t equals 20 minutes. All right, t equals 20 minutes. So the amount of salt in the tank at the moment of overflow can be easily computed. So amount of the salt at the moment of overflow. So it's simple that time is 20, so 2 times 20 squared plus 20 times 20 divided by 20 plus 5. That will give us 48 pounds. So the amount of salt in the tank at the time of the overflow will be 48 pounds, right? So that's all for the time being. Hope you guys understand this problem, and we'll come up with more problems in the next class. Thanks for the time.